Welcome everyone. Today we are going to talk about something really important. How to keep your PostgreSQL databases safe on Debian Linux using SSL and TLS. Whether you are brand new to databases or just new to security, this guide will walk you through everything step by step in simple language. By the end, you'll understand what SSL and TLS mean, why they matter, and exactly how to turn them on for your databases. Let's start with the basics. You've probably heard the terms SSL and TLS used together sometimes. People even say SSL, they mean TLS. Here's the simple explanation. SSL or Secure Socket Layers was the original technology invented in the 1990s to encrypt internet connections. However, it had security problems, so it was replaced. TLS or Transport Layer Security is a modern replacement. Today, systems use TLS version 1.2 or 1.3. When people say, let me set up SSL for my database, what they really mean is, let me set up TLS. Think of it like this. SSL was the old door lock, TLS is the new, much stronger one. The key idea is both are about scrambling your data so nobody can read it in transit. So, why does this matter? Why should you care? Here's a scary fact. Without SSL, when your application talks to a PostgreSQL, all that communication travels as plain readable text across the network. That includes your database passwords, your SQL queries, and your users' data. Anyone who can interpret that network traffic, maybe another machine on the same Wi-Fi, or a hacker on a shared server, can read everything. With SSL turned on, all of that becomes encrypted garbage to anyone looking. Only the two ends of the connection, your app and your database, can understand it. If you're running a database that handles any real user data, especially in the cloud or in a VPS, SSL is not optional, it's essential. And how it works. Now let's understand how SSL actually works using a simple real-world analogy. First, there's a certificate authority. Think of this like a government passport office. It uses and stamps certificates. Second, your PostgreSQL server gets its own certificate, its ID card. Third, the ID card has a private key attached, like a secret pin that only your server knows. When your app tries to connect, they do a handshake, like two people agreeing on a secret code before talking. After that handshake, they both agreed on an encryption key, and from that point on, all communication travels in a locked box. The whole handshake takes milliseconds and happens automatically every single time. Right. So let's get into the overview or the implementation steps. Here is a roadmap for the next few slides. We'll go through three phases. Phase one is would be creating the certificates. We'll use a tool called OpenSSL to generate all the files we need. Phase two would be the configuring PostgreSQL, where to configure files to switch SSL on until it where the certificate files are live. Phase three is testing. We restart the service and verify that encrypted connections are actually working. Don't worry if any of those sounds unfamiliar. We'll walk through every single command, what it does and why. So let's first command create something called a certificate authority of CA. This is your own personal stamp maker that will later approve and send your server certificate. The command is, as you can see, the command. Let's break it down. OpenSSL request opens the OpenSSL request tool. Think of opening the passport office application. And new means that it has to start fresh. The X50 means make this self-signed certificate, meaning the CA approves itself because it is the top authority. And we can also mention the days with 3650 as the 10 years valid. And nodes means it would be a no password for the key file, which is easier for automated servers. The out file ca.certificate saves the certificate to a file called ca.cert. The key ca.key saves the secret key to ca.key. After this command, you'll have two files, ca.certificate file and ca.key. Now we generate the server's own identity. There are two parts here. First, the private key. This is the server's personal secret. Second, the CSR, which stands for Certificate Signing Request. Think of it as a job application form. The server fills in its name and hands this form to a certificate authority, saying, please give me an official certificate. The command is, as you can see the command, and you'll replace the DB host with your actual server's hostname or IP address. After this, you have server.key and you should never leave this server.key and the server.csr application form to give it to the CA. On the 8th slide, we had the application form to the CA to get the official certificate issued. The command is, we have the command below, and we'll walk through each command and the parameter that itself define everything. The X5 run means we are working with a new certificate. Request means we are reading a signing request. Server.cr is the application form from the previous step. ca.crt uses RCA to approve this. CA.key is the secret key, that's the signing pen. And CA create serial gives the certificate a unique serial number like an ID number. And the certificate server.crt is the out file, which is the final approved certificate. And you can also mention the days, which means it has to last for 1 year with the 365 as the number. And you'll need to renew it annually. After this command, you now have a server.certificate, the official identity card for your PostgreSQL server. And we have the step number 4, copying files and getting the permissions. Now we'll have all the three files ca.cert, server.cert, and server.key. We need to put them in the right place and lock them down. The first command uses cp, which just means copy, to move those three files into the PostgreSQL home directory on Debian, which is the /etc/PostgreSQL/89 main. The second command changing the ownership of the secret file to the Postgres system user. PostgreSQL runs as this user, so it needs to own the file to read it. The third command is using the chmod command line argument with cn600 sets a permission so that only the owner, the Postgres user, can read or write the key file. Nobody else can touch it. This is critical for security. The private key must stay private. And on the step 5, we are configuring the PostgreSQL. We edit two configuration files in PostgreSQL. The first is the PostgreSQL.conf. This is the main configuration file. We add 4 lines SSL equals to be on. This tells PostgreSQL to non encryption. Then we point it to our 3 files: SSL cert file for server certificate, SSL key file for the private key, and SSL CA file for the certificate authority certificate. The second file is the pghba.conf. This is PostgreSQL guest list. It controls who is allowed to connect and how. We add a line with post SSL, which means only accept connections that are encrypted. All means for all databases and users, we have to give the all IP so that anyone can connect to that. We use the scram SHA password here for the verification, and together these two files are your control plane. One turns on SSL and the other makes it mandatory. And on the 11th slide, this is the sixth step. We're going to restart and verify what we have almost done. There are 3 final steps. First, restart the PostgreSQL with the command, and this stops the server and starts it again with the new SSL settings loaded. Without this restart, PostgreSQL is still running the old configurations. Second, test your connection from a client using the pSQL with 2 important options. SSL mode should be verifiable, which means the client will insist on both encryption and certificate verification, and SSL root cert pointing to your ca.cert file, so pSQL knows which CA to trust. Third, once connected, run this SQL query against the pgstat SSL view. It will return a row showing SSL equals true, the TLS version being used, and the cipher name. If you see this, SSL is fully working. Now, yep, that's the recap what we have done so far. Let's take a moment to appreciate what we have done. We started from the zero and built a complete SSL and TLS encryption setup for our PostgreSQL database. Step 1, we have created our own certificate authority, and later on we have generated the server's private key and a signing request. And in the step 3, we had the CA officially approved and signed the server certificate, and we placed all the files in the right configuration or location with the right permissions, and we told the PostgreSQL to use the SSL via PostgreSQL conf file, and we made SSL mandatory in pghba.conf file with the host SSL option. And in the last step, we have restarted the service and confirmed it's working, and every connection with our PostgreSQL 18 database is now fully encrypted. That's a real production level security setup. Well done. That's it for the class today. We'll move on to next class or next lecture. Thanks.